Welcome everybody. We're going to do a AIA presentation here with Mike Rayleigh, he's our Director of Engineering, and he's going to give you some up-to-the-date stuff on acoustics. So without further ado, Mike, I'll let you take it away.
Okay, yeah, thank you so much for joining us. Just a few housekeeping things before we get going. We've got quite a few folks here today. Please make sure you keep yourselves muted. If you have any questions, there's a Q&A function. You can throw your questions in there as we go through the presentation, and then when we're done, we'll have time at the end where we can come back and address those questions. And also, at that point, feel free to raise your hand, unmute yourself, and just ask a question live too. Also, I think most of you got here by registering through AEC Daily, getting that link. Hopefully, if you want AIA credits, you put in your AIA number when you registered. If you didn't go through that process for any reason and you do want AIA credits, please do reach out to us. You can shoot us a message in the chat, the Q&A, or contact us afterwards, the email or something like that. We want to make sure you get your credit, get credit for spending time here with us today. So I think that's everything. And so now I'll go ahead and get started. So today's presentation is titled Better Design Through a Deeper Understanding of Acoustic Ratings. And I'm going to talk about two acoustic ratings that are probably familiar to many of y'all. That would be the STC and the IIC ratings. And I'm going to talk a little bit more in detail about what they are, how they're measured, how they're actually calculated. We're going to kind of, look under the hood of those ratings. And then we're going to talk about two fairly new acoustical ratings, the HIIC and LIIC, and explain what they are and kind of how they might help us. So let's get into it here. So we're going to start out with kind of the basics of STC and IIC, what they are. And then we're going to talk about some of the differences between lab and field measurements. Then we'll get into just a few myths and misconceptions about the STC and IIC ratings, things that I've come across over the years of working as a consultant and an engineer for noise control product manufacturers. Excuse me. And then we're going to get a little more technical. We're going to get into actually reading STC and IIC graphs. And the reason I'm presenting this is to help everyone understand a little bit more of what goes into those, because that helps understand some of the limitations and hopefully helps better inform how we use those ratings for designs and buildings for noise control. And along those lines, we'll talk about how the STC and IIC ratings are actually calculated. And then from that discussion, we'll talk about some of their shortcomings, where they do and don't apply, how well they actually work as design tools. And then from that, we'll get into these two new ratings, the HIIC and the LIIC, that deal with impact sound, just like the IIC rating. And last but not least, right, we'll talk about all these ratings and all this kind of technical stuff. But at the end of the day, we want to design quieter buildings, right? So we'll talk about methods of improvement for noise control and use these ratings that we've talked about to kind of look at those different methods of improvement and where they make differences and maybe where they don't. So before we get into all of this, a lot of times we're looking at noise control because of code requirements. That's especially true in multifamily, right, where the International Building Code has requirements for STC and IIC ratings, right? So I want to start out the discussion with this quote. That is that with the current level of performance specified by the building code, a large percentage of people are highly annoyed by noises from their neighbors, leading to a reduced quality of life and possibly to negative health effects, right? So that's, if you just the code minimum, a large percentage of people are highly annoyed. And, noise can create stress. Stress is a big health factor. So noise can really have an adverse impact on our health. So you might think, this quote is from, some acoustician or something like that, or product manufacturer trying to sell more stuff, but it's actually from the International Code Council themselves. And this is from a sort of supplementary document, the ICC G2 2010 Guidelines for Acoustics. It's a good reference. If you're not familiar with it, I'd suggest you go Google it, check it out. It's a good reference to have in your files. Okay, so the basics, STC and IIC, what are they? What's the difference? Where do they apply? So we'll start with STC, which stands for Sound Transmission Class, and it measures the reduction of airborne sound. And we're talking about airborne sound. Really, what we're talking about is sort of where the sound originates. So it originates with an interaction with the air. So speaking would be an example of that. Sound from a TV or a stereo would be other examples. Whereas for IIC, we'll talk about is structure-borne sound, and that originates with interactions with the structure. So STC is airborne sound. It applies to walls and floor ceiling assemblies. Noise source examples, which I already mentioned, are talking, TV, and stereo. Could be dogs barking, other things like that, right? And the way we measure an STC rating is, so in a laboratory environment, we have these two separate rooms, and we go to great lengths to sort of isolate those rooms from each other acoustically. And the idea being is that when we're doing our sound measurement, all we're measuring is the sound that's going through the partition. In reality, it doesn't always quite work out as well as that, but that's the general idea, is that we're measuring just the sound that's coming through the partition that we're testing. So for a wall test, we have two rooms that are next to each other. There's a hole between them, and we build our wall in that in order to test it. Similar thing for floor ceiling assemblies, except that the rooms are stacked on top of each other, and we build our floor ceiling assembly in a hole between the two rooms. And here we have the source room. We got some speakers in it. We make a bunch of noise. We measure how loud it is. In the receive room, we also measure how loud it is. We take the difference between those two. That gives us sort of our noise reduction. And then we do some calculations and we get an STC rating. The IIC stands for Impact Insulation Class, and it measures the reduction of structure-borne sound. And when we're talking about structure-borne sound, we mean sound that originates with an interaction with the structure. So the most common example of this would be footsteps, right? We step on the floor, we step on the structure, and we create sound. Other examples could be, a piece of mechanical equipment or something like that that's, tied into the structure that makes the structure vibrate. And the IIC rating only applies to floor ceiling structures. We don't do IIC measurements for walls here in the United States. Noise source examples would be footsteps, dragged chairs, dropped objects, vacuum cleaner rolling around, those different kinds of things. And the way we measure it is we have a standardized impact source, which is the tapping machine. You can see a picture of one there at the top. And that machine has these little metal weights that are cam operated usually. They're dropped onto the floor. So you get this tap, 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 tap on the floor. And then you measure how loud it is down below. And you do some calculations and you get an IIC rating. So now, what's the difference between a laboratory measurement and a field measurement? Because we have standards for airborne and structure-borne sound isolation measurements for both the laboratory and for the field. So first, the metrics. For airborne sound, it's the STC rating, right? For impact sound, it's the IIC. You'll see those referenced in the building code and a lot of other sort of code requirements and things. In the lab, the idea is that the flanking paths are controlled or eliminated, and the flanking paths are other ways that the sound can get from one space to another, going around the assembly that we're trying to test. So since we've controlled that flanking sound, then the test really only measures the sound that's going directly through the assembly. Now, there's limitations to this, but that's a conversation for another time. But then the hope is that the results indicate the performance of that assembly independent of the surrounding structure. So we know what this wall is doing, sort of regardless of the context. Field is different. So first, we'll start with the metrics. So for airborne sound, we have ASTC, NNIC, and NIC. They're all basically measured the same way as an STC rating. You make noise in this room, measure how loud it is, measure how loud it is down here, take the difference, do some calculations, right? The difference between those three metrics is really just sort of room conditions and some kind of nuanced stuff like that. Impact sound, we have a similar situation, three different metrics, AIIC, NISR, and ISR. And again, they're all measured the same way with the tapping machine. It's just sort of room conditions and things like that that differentiate between the different metrics. In the field, though flanking past, those other ways that the sound can move from space to space, they're included. Because in the lab, we isolate these buildings, but and we're just getting the direct path. But in the real world, all these rooms are connected to each other. They're tied to each other structurally. So the sound can travel all these other ways from room to room that sort of go around the assembly that we're testing. So when we go and we do a measurement in the field, the results indicate the performance of the assembly, but also the surrounding structure. And this means that the results are only applicable to that tested assembly in that specific space, right? Context really matters. So even in the same building with the same basic, floor ceiling assembly, we could measure it on, one apartment unit on this floor and another apartment unit on that same floor, but the structural connections, the way things are framed, all of those different things might vary between those two spaces, and those will affect the results that you get. So you can't take this result here necessarily and apply it somewhere else in the building. And it's certainly difficult to take that result and really accurately extrapolate to some other building and have a good idea of what you're going to get there. So field measurements are really good at identifying what's going on at that specific space, but less indicative of what you'll get somewhere else. So code requirements, right? Beginning, we talked about the codes, not enough, but what are the code requirements? So this is for multifamily housing from the International Building Code, right? For airborne sound, if it's a laboratory measurement, it's a minimum of 50, so that would be an STC 50. And in the field, it's a minimum of 45. Now, actually, until the latest code cycle, they didn't actually specify which one of those metrics you're supposed to use for a field measurement. Now, in the latest one, I believe that it's specified in an IIC for airborne sound. For structure-borne sound, the numbers are the same. For lab, it's a 50. That would be an IIC 50. And in the field, it's a 45. And again, previous code cycles, they hadn't specified the metric. Now I believe it's the NISR that's the field rating. And actually on these, so I mentioned that ICC guideline document. That document includes recommendations for higher performance levels, like higher tiers above just the code minimums. Okay, let's get into some myths and misconceptions. So again, these are things that I've kind of come across, questions I've been asked, or things people have talked to me about over the years as I've worked as an acoustician. So the first one would be you can add STC ratings. So we'll take a pretty basic example here. This is a 2x10 floor ceiling assembly. And here in this first instance of it, we have just the 2x10s, some bad insulation in the cavities, and a subfloor, plywood or OSB wood subfloor. And the bottom side of the joist is exposed. There's no ceiling here, so the joist cavity is exposed to below. And when you test that, these are actual test results from a Canadian research document from the National Research Council of Canada, get an STC 24. If you sort of do the opposite, you take the 2x10s and apply just the ceiling with nothing on the top side. We've got gypsum board on resilient channels. You get an STC 27. So we've got these two separate elements, right? Can we just sort of take this data, add it together, and build an assembly and get what the total rating would be? If you add these two, you get an STC 51. Well, from that same report, when they actually went and tested that assembly with those layers put together on the top and bottom, they got an STC 49. That's only a 2-point difference, which I know isn't that big of a deal. But in this case, it made the difference between, the added STC rating says, okay, this thing will meet code. But when you actually go test it, it doesn't. It's below that STC 50 code minimum. So even though it's a small difference, it's a difference that could get you into trouble, right? That creates this liability, creates potential issues. And we could come up with other examples that are much more extreme in terms of the difference in the ratings. So if you think of a single stud wood wall, single 2x4 wood studs, a layer of gypsum board on each side, might be around an STC 36. So take another one of those and stick it right next to it, right? So now you've got two walls with an airspace in between. Can we add the STC ratings and get an STC 72, 36 plus 36? Not at all. If you actually go measure that, I think it's something more like an STC 46, right? So again, you add the STC ratings, you get something that's over code, but when you actually go test it, it might very well be below code. So really what you have to do is test the whole assembly. In a similar vein, there's this idea that you can add a delta IIC to any assembly. So what is a delta IIC? So the IIC is a measurement of impact noise reduction for the space down below, right? The delta IIC is the change in that IIC rating. And the way we measure it is it's always done on a concrete slab. Usually it's a 6-inch thick concrete slab. And we measure the IIC of the bare concrete slab, and then we put some flooring and underlayment on it, and we measure the IIC again. And we take the difference, and that's basically our delta IIC. So it's the improvement in the IIC rating of a concrete slab for some floor and underlayment combination. So here we have, I think this is engineered wood flooring on a thin recycled rubber mat, and it got a delta IIC of 24 on a 6-inch concrete slab. So then can we take that delta and apply it to some other assembly? Here we have an open web truss. It's got a thick layer of gypsum concrete on the top on a sound isolation mat. On the bottom, we have sound isolation clips and 2 layers of gypsum board. And this assembly, without any flooring and underlayment on the top side, already has a very good rating of IIC 62. Can we add them and get an 86? That would be fantastic. That's a really high, awesome IIC rating. But unfortunately, you get a 68 when you actually go measure this assembly. Now, 68 is still a really high IIC rating, but it's nowhere close to 86. So again, you can't just take this delta and apply it to any assembly. And the reason is it's tested on a concrete slab. A concrete slab behaves very differently acoustically from a lightweight wood structure like an open web truss. And last but not least, this sort of idea that acoustical products have their own STC or IIC ratings. There are some instances where products do sort of have their own acoustical rating, again, sort of removed from the context in which they're used. So NRC values, CAC values for acoustical ceiling tiles kind of fall closer into that. Sound absorption measurement, NRC values are closer to that, more of just like a material property rather than like an assembly property. But for STC and IIC ratings, we're measuring an entire assembly. And so the individual elements don't have their own ratings. So here's an example of that. We've got two 2x4 wood stud walls. All of the elements within these are the same, right? We've got 2x4 wood studs. We've got fiberglass bad insulation. We've got some sound isolation clips that isolate the gypsum board from the studs. And then we have the gypsum board. The only difference here is the number of layers of gypsum board, but that makes a 6-point difference in the STC rating. So like the clips themselves don't have an STC rating. It depends on the structure of the assembly that they're used within. Okay, so we've got the basics of STC and IIC. We've got some myths and misconceptions. And now we're going to get into some more of the technical stuff and really talk about reading these graphs. So if you've ever gotten an acoustical, like a laboratory test report for some acoustical product for an assembly, if you've looked through it, you should have seen a graph like this here on the right. So this is the measurement data and sort of the process that goes into coming up with an STC or an IIC rating. And this tells us a lot more information about the performance of the assembly. When we're looking at IIC ratings and IIC tests, what we see on this graph are ISPL levels, ISPLs in decibels. ISPL stands for impact sound pressure level. And really that's just how loud are the impacts in the space below the assembly. So when we're tapping on it on the top, how loud is it down below? When we're doing an STC test, what we get in this graph is the TL in decibels. It stands for transmission loss. And really what it tells us is how much does the assembly reduce the noise levels from this side to this side, right? From the source side to the receiver. So to read this graph, on the horizontal axis or the x-axis, we have frequency in hertz. Low numbers down to like 100 hertz on the left side are low frequencies. A musician, I like to use the bass as an example, right, of low frequencies. Oops, let me click over here. And then high numbers are high frequencies. So you can think of a violin as the example of higher frequencies compared to an upright bass, double bass. Another way of thinking it, low frequencies, think of a diesel freight train, right? That like rumble that just goes right through walls, that you almost like feel it as much as you hear it. And then for high frequencies, think of like that shrill, piercing sound of a fire alarm, a backup beeper, your timer on your oven, those kinds of things. Those tend to be higher frequencies. And as I was looking for information, I found that some fire alarms like this, at least, I think it's a standard that they output a tone at 3,150 hertz, which is the upper limit of the IIC calculation. So maybe it gives you a little bit of idea of what that frequency actually is. So when we're looking at these different frequencies here at the bottom of this graph on the x-axis, we can sort of think of these frequencies as like keys on a piano. And the keys on a piano, right, are all different musical notes, and each musical note has a different frequency. So when we're looking at this, it's kind of like how loud are we hitting each one of those keys on the piano to create the total sound of what this assembly is like when we're tapping on it or playing sound through it. And just as an aside, bonus points to anybody here who's paying attention and can identify the issue with this piano. You can stick it in the chat or the Q&A. Okay, so we've gone and we go to the lab and we do a measurement, or we do it in the field. The calculation process is pretty much the same. So let's take an STC test, which is represented by the graph here on the left. So we've gone, we make a bunch of noise in one room, we measure how loud it is, measure how loud it is in the other space, take the differences, and that basically gives us our transmission loss, or our TL values. So then you plot those TL values on this graph, and that's the gray line here, right? So again, we're going from low frequency at the left to high frequency at the right. And in this case, higher levels mean more noise reduction, right? Which is good. So bigger numbers are better here. But we've got these values at all these different frequencies. How do we take that and turn it into a single number STC rating? And the way we do that, the method, is what's called a curve fit. So we have this curve represented by the orange line that's specified within the standard. And you compare that orange curve to the measured values. And we shift that curve up. And anywhere where the curve, the orange line, is above the measured values, we call it a deficiency. It doesn't mean that the wall is bad. It just means that the curve fit is above the measured values. And so you can see as we kind of cycle through this here, as that orange line shifts up, you see down at the bottom of the graph, those yellow bars creep up. Those are the deficiencies. And we're looking for two criteria here, and that is that the sum of the deficiencies, when you add all those yellow bars up, that sum can't exceed 32. And the maximum deficiency at any one frequency can't exceed 8. And if you go above either of those, you got to bump it back down a level, and you max out your deficiencies without exceeding those thresholds. That gives you your STC rating. So it's a little convoluted to kind of how we get to this, right? The IIC calculation is very similar. We just kind of shift things the opposite direction. So for the IIC, if you remember, we tap on the floor up above and we measure how loud it is down below. So for this, our impact sound pressure levels, or ISPLs, lower numbers are better because it means it's quieter. So here we're shifting the curve down, which represents higher and higher IIC values. And again, we're looking at the difference between the measured values and that orange line. Those are deficiencies. We have the same criteria, a sum of 32, a max of 8. And that gives us our ratings. But you could think about how these curves might be different shapes, and you might have deficiencies at different places. And if some frequencies are louder than others, the assemblies might sound different, but you might still get the same rating. When I've presented these graphs to people in the past and I've tried to explain them, one of the questions a lot of people have had is, well, wait, how do you have all of those frequencies at the same time? And one sort of analogy or example that I gave is it's just like taking your arms and just smashing all the keys on a piano, right? You're playing all of those notes, right? All of those different frequencies at the same time, and some are louder than others. That's kind of the same thing that's happening when we're going and doing these STC and IIC tests. But sometimes it's still a little hard for people to kind of wrap their minds around. So another demonstration that I've done is this, which is called a spectrogram. And there's a link at the bottom where you can actually go do this. It's live. You can use your like computer microphone, and it actually scrolls through and like shows up these color charts, the spectrogram, as you're talking, making noise, singing, whatever you want to do. And I think it really helps understand like frequency and level and some of these acoustic concepts. So here on this, we've got a keyboard up at the top, lower frequencies to the left, higher frequencies to the right. And what you get here, this is kind of like a thermal imagery, right? Where red is really hot, black would be cold. In this case, red is loud, black is quiet. And so you can see the sound levels at different frequencies. So in this case, I think I was just like, tapping a pencil lead or something like that on my desk, or tapping my nails. So this kind of very high frequency clicking sound. And that was this first circle here, right? And then this other one was like pounding my fist, thumping. So you can see like the sound looks different, and that's the different frequency content. That's the same kind of thing that we're getting with those graphs for the STC and IIC tests. All right, so shortcomings. We've got the standard, or both of these standards, the STC and the IIC standards, and then their sort of field equivalents. They've been around for many years, but they have some shortcomings. And part of that comes from what they were originally designed for. So the STC rating was originally designed around speech. And at the time when it was developed, we didn't have sound bars, right? We didn't have big 7.1 channel home theater systems. There was a lot less sort of electronic sound reproduction that could create lower frequency things that was an issue in multifamily housing and these kinds of places. So developing around speech made sense at the time. But now we have a lot of things that go outside of that speech frequency range. So because it was developed for speech, we have a limited frequency range. So here's another one of those graphs, right? Remember, the x-axis is frequency. So we go from the low frequency at 125 hertz to the high at 4,000. This is the sound frequency range that we measure and use to calculate an STC rating. But here's what we can hear. This is what we measure, but this is what we can hear. And if you look at this, you see that, remember, the gray line is what we measured. These are the transmission loss, or sort of the noise reduction values that we measured. And generally, as you go up in frequency, bigger numbers, the transmission loss increases. So where that orange line ends at 4,000 hertz, if we're doing good there, we're probably going to be as good or better, have as much or more noise reduction at the higher frequencies. But when we go down to the low end, over towards the left, the orange curve ends at 125. But we've got this actual data, the gray line below that, and the TL values keep going down. So just because maybe we're good at 125 with the amount of noise reduction that we get, it doesn't mean that we will be at 100 hertz or 80 hertz or further down. And that becomes really important when we have spaces that create a lot of low frequency energy. That might be a movie theater, right, with big subwoofers. It might be a music venue, or it could be a spin class, right, where the instructor wants to be really loud and they've got a PA system with a subwoofer, right? Or it could even be a home, even a little sound bar, right, to go along with your TV. Those can still produce significant sound energy. They can be fairly loud below 125 hertz. But the STC rating doesn't tell us anything about that. It also doesn't tell us about the noise reduction at these different frequencies. So if we care about some particular frequency range, like lower frequencies, the STC rating doesn't really tell us what's going on down there specifically. So it doesn't tell us the whole story. It gives us sort of an overall number, but it doesn't tell us about the characteristic of the sound. Hang on a second while I just mute folks here. So also going back to that original quote, right? The code minimum does not guarantee satisfaction. Part of that is because of this limited frequency range. If you have a noise source that's making significant sound outside that frequency range, STC rating isn't necessarily going to help with it. But also if you have something that's particularly loud, like a spin class or something, the code minimum might not do it. Or if you have high expectations for sound reduction, like in high-end condominiums, the code minimum, it's a minimum. It's not necessarily enough to meet those expectations. So IIC. We have some similar things here. So the IIC was designed around footsteps. And in multifamily housing, I think in large part, footsteps are probably still the biggest or one of the biggest sources of complaints for, structure-borne sound. And the frequency content, the characteristics of that sound, I don't think have changed too much over the years in terms of the way we walk. But it does still have a limited frequency range. Here for IICs, we go from 100 hertz, the low end, to 3,150 hertz at the high end. And again, here's the range of what we can hear. So what we measure, what we can actually hear. And again, here, if you look at the gray line, you can see we've got it extending out beyond the orange line, which represents, sort of the bounds of the IIC calculation. And for the transmission loss, the graph went up with frequency. For IIC, for the impact sound pressure levels, the graph goes down with frequency. So that means as we go higher in frequency, it gets quieter. As we go lower in frequency, it gets louder. So again, if we're good at the lower limit, 100 hertz for the IIC, it doesn't mean that we're going to be quiet enough at 80 hertz or 63 hertz, right? But at the high end, if we're good at 3,150 hertz, we're probably going to be okay at the higher frequencies too. And in the STC rating, we'll see some changes in the shapes of those curves, which really sort of mean like different characteristic sounds. They'll sound a little different. But in the IIC ratings, we can see big variations in the shape of these curves. So, and what that means is it'll sound different. Some frequencies or some assemblies, some floor ceiling assemblies, you might get more low frequency, more thumps and thuds from impacts, and others you might get more high frequency, more sort of clicks and clacks. And it just depends on the structure and a bunch of different sort of elements. And again, the code minimum does not guarantee satisfaction. And I think that is more so the case with IIC than it is with STC. And as an example of that, here's a sort of a case study. So this is a report that's often referenced within the acoustical community when we're talking about, IIC ratings especially. And it's from the Journal of the Acoustical Society of America back in 1994. And it's written by Blazier and Dupree. And it focuses on a large luxury condominium building in the San Francisco area where there is a big class action lawsuit. It was $80 million that was brought against the developers. And a major claim in that was about annoyance from excessive noise and vibration from footsteps. So the kinds of things that we try to get at with the IIC rating. And when we're looking for, designing floor ceiling assemblies, getting good IIC ratings, carpet and pad will typically give us very high IIC ratings, into the 60s, 70s, or maybe even the 80s, depending on the structure that it's on. And a lot of times we think that, oh, okay, we've got this really high IIC rating. That's good, right? If we've got carpet and pad, we're fine. It's the other areas with hard surface floors that we need to worry about. But in this case, the complaints came from areas without carpet, but also areas with carpet. And the reason for the complaints was primarily thuds, thumps, and booming. So the low frequency stuff. And sometimes the carpet doesn't always help on that, or it doesn't make it good enough, right? And here's a great quote from this, right? So the IIC rating of a floor system is meaningless with respect to the perception of these low frequency components, the thumps and thuds, of footfall noise, because the methodology ignores the frequency spectrum below 100 hertz. So when we talk about limitations of the STC rating, it's designed around speech, so it's got this limited frequency range, but we don't really produce, when we're speaking, a bunch of sound outside that range. But for footsteps, the IIC rating ends at 100 hertz, but our footsteps might very well produce significant noise below 100 hertz, but that's ignored by the IIC rating. So I talked about how for the IIC, you measure those sound pressure levels and you get this curve, right? And those curves can vary significantly. So here we have a bunch of different assemblies that were measured. So each colored line on this represents the measurements of the impact sound pressure levels for an assembly. So we have a bunch of different assemblies here that were tested. And all of these were an IIC 55. So they got the exact same IIC rating. But if you look at the curves, like those all sound very different. So here's the range for IIC. So even within that range, there's still big variation. And if we look at the low end at 100 hertz, the minimum level measured was 52 dB and the maximum was 65 dB. So it's a 13 dB difference. And for some context, a 10 dB increase is a doubling in perceived loudness. So at 100 hertz, the loudest assembly here was more than twice as loud compared to the quietest assembly. That's a big difference, but they got the same IIC rating. If we look at the high frequency, if we look at the high frequencies at 3,150 hertz, it's an even bigger range. We go from a minimum of 5 dB, just sort of barely above the threshold of hearing, to a maximum of 45 dB, so a 40 dB range. So if you could go into the room and stand below and listen to the impacts on each one of these assemblies, they would sound very different, most likely, but they all get the same IIC rating. And when we're in a space and we've got our neighbor upstairs stomping around, what we respond to is not the IIC rating. What we respond to is the characteristic of that sound. Are there clicks and clacks or are there thumps and thuds? And how loud are those different components? So to try to get at some of those issues, some folks at Vinna Clausen, an acoustical consulting firm out of California, have worked to develop these two new standards and put them through ASTM, the standards organization, and they have now been approved. And these ratings are the HIIC and the LIIC. So HIIC stands for High Frequency Impact Insulation Class. It's in standard ASTM E3222, and it really gets at the clicks and clacks. So you think about like, high heels on a hard surface, or hard-soled like dress shoes, or dog's nails, those kinds of things. And it's this range highlighted here from 400 to 3,150 hertz. LIIC stands for Low Frequency Impact Insulation Class. It's ASTM E3207, deals with thuds and thumps from impacts, and it's this range from 50 to 80 hertz. So the HIIC is within the range that we're already measuring and using for the IIC calculation. The LIIC is outside of that range. It gets at those thumps and thuds, that low frequency stuff that Blazier and Dupree said were really important but are ignored by the IIC rating. So what do we use these for? Well, the HIIC is easily measured as part of an IIC test because it's the frequency range that we're already dealing with. And you can also calculate it from older IIC test data that was taken before the HIIC standard existed. You can just go back and recalculate based on the data. But if it stays within that IIC range, like what's the point? So what the folks at Vinna Clausen found is that when you change out the flooring and underlayment on a particular assembly, the flooring and underlayment tend to not do much at the lower frequency stuff, but they can make big differences at this higher frequency range. And so the HIIC can do a good job of differentiating between different flooring and underlayment combinations. And that can be particularly useful, say you've got an existing condo building where people are, new people are moving in, or existing owners want to renovate their condos, they want to put in new flooring, right? So a lot of times the CC&Rs for those condos will have IIC requirements. The IIC depends a lot on the building structure itself. And I've run across many instances where those IIC requirements within the CC&Rs are unobtainable because of the existing building structure that the owner can't do anything about. And HIIC can help you sort of differentiate between the different flooring and underlayments in a way that's really more applicable and realistic for that situation. The HIIC can also help differentiate between ceiling isolators and their level of performance at those higher frequencies. LIIC is a completely different animal. So it's outside the measured range for IIC, right? Represented by that orange bar, orange line. So you can't always go back and calculate it from older tests. The LIIC is also rarely affected by flooring and underlayment. Ceiling isolation can affect it. Also, your building structure, the stiffness of the structure, the mass of the structure play a big part in your LIIC rating. So it can be useful for evaluating, structures and also ceiling isolators. It's hard to measure because of the low frequency range, and there's a lot of physics that sort of gets into why that is. I'll spare you that. But the important things to know about the LIIC rating is that it has lower accuracy and precision. There's a difference. You can go Wikipedia it if you don't know. And the LIIC, there's unknown and probably low correlation between labs. So if we take an assembly and we measure its LIIC in this lab, and we build the same assembly in this other lab, we might get very different LIIC ratings. There's also unknown and probably low correlation between the lab and the field. So if we measure this assembly in the lab, we get some LIIC rating. We go build it in our building, we might get a very different LIIC rating. So, and what on earth is the point of this? Right now, what the LIIC rating is, I think, most useful for is apples to apples comparisons, back-to-back comparisons in the same lab, or in the field if you can go do mock-ups and do testing that way. So in the lab, say you're changing out ceiling isolators, or you're adding a layer of gypsum board, or you're looking at changing, your topping of gypsum concrete or something like that, and you're doing these tests back to back in the same lab. If you see a significant difference in the LIIC rating, that's probably indicative of what's happening at low frequencies, and you can expect some kind of similar, change in the field. But your absolute values might be different, but sort of the relative change is going to be there, right? All right, so last but not least, we've gone through all of this kind of wonky stuff, all the technical details of the ratings, their limitations, all of this. But at the end of the day, we want to design better buildings, right? Buildings that are quieter. So how do we use these tools to do that? So let's look at flooring and underlayments first. So for all of these, I'll have two assemblies. The upper assembly would be the base, and the lower assembly has whatever the change is. And I've presented the STC, IIC, HIIC, and LIIC ratings for all of these. And we'll see how they change. So this is a open web truss assembly, pretty standard. And the only thing we've changed is on the bottom, we've added flooring and underlayment. So you can see the STC rating goes down a point. It's really insignificant, kind of within test variability. The IIC rating goes up 12 points. That's significant. HIIC goes up 22 points. So here you can see, like I was saying, the flooring and underlayment can really make big differences at those higher frequencies. Whereas for the low frequencies, the LIIC, that rating actually went down from a 51 to a 48. Like I said, less accuracy, less precision. Maybe the flooring made it worse. Maybe there's just variability here. It certainly didn't make it better. So, lots of good stuff going on at the HIIC, the higher frequencies, the IIC, that wider range, but at the really low frequencies, flooring and underlayment certainly not helping. Okay, so ceiling isolators is another way, right? We can use some sort of sound isolators for our ceiling to improve our acoustical ratings. So here again, we have this open web truss assembly. This time, both of them have the flooring and underlayment. The one on the bottom has just added these rubber isolators to the resilient channel to try and improve the performance. So STC rating went up a point, again, negligible. The IIC rating went up 5 points. That's significant. That's sort of if you look at that ICC guidelines document, a 5-point improvement is like up to the next tier of, sort of acoustical performance. The HIIC also went up 5 points. So we're getting high frequency improvements. The LIIC went up 6 points. And that's 6 points is significant. These tests were done same lab, right? Same assembly. So, that shows that, yes, this ceiling isolator is improving the low frequency and the high frequency impact sound isolation. Mass, right? Mass is another way that we can improve the amount of noise reduction we get from space to space. And it's just the heavier the thing is, it's harder for the noise on one side to move it and to get through to the other side, basically. So here's a basic example of a 6-inch slab compared to a 10-inch concrete slab. And you can see that all of the ratings go up, and they all go up by, about 5 points, except the LIIC actually goes up by 9. So mass can be a good tool, and it's what we're doing when we're adding an additional layer of gypsum board to a ceiling or to the sides of a wall, right? We're increasing the mass. But we have this mass law that says when you double the mass, you get about a 6 dB improvement, in your change in your sound reduction or impact levels, whatever it may be, right? If you double the mass of the assembly. So obviously that adds up pretty quick, right? If we've got a wall with a single layer of gypsum board on each side, it's easy to double mass, just add another layer of gypsum board. But to double the mass again, you got to add 2 more layers, and then you got to go 4, right? So that gets prohibitive pretty quickly. So it can be a good tool, but it has its limitations. Insulation is another thing that we can use. And if you think about going into some sort of, modern design, fast food space or something like that, right? It's all hard surfaces, polished concrete floor, gypsum board walls, a lot of glass, exposed metal deck, right? All hard surfaces. It doesn't take many people talking in there for that sound to build up really quickly. And what happens is there's nothing to absorb that sound energy, so it just hits the walls and it keeps bouncing off. We've got this big reverberant space, the sound just builds up in it. When we have an assembly like this open web truss, we create this space inside of it, right? We create this cavity between the plywood and the gypsum board. Well, those are both pretty hard surfaces. So we've created this reverberant space where the sound can just keep bouncing around and build up in there. And when we add the insulation into that cavity, it's the same thing as like adding hard, soft surfaces, acoustical absorbers into that like restaurant space, right? It quiets it down because it absorbs that sound that's bouncing around. It's the same thing that goes on in these assemblies. So the insulation is not blocking the transmission of sound. That's another common misunderstanding. It's just absorbing, reducing the sound that's bouncing around inside this space. So here we've added insulation to this. We see an improvement in the STC, the IIC, the HIIC, and the LIIC. So it's effective for both airborne and structure-borne sound and across a wide frequency range. There are limitations to this. If you go from no insulation to some insulation, you tend to get a pretty big jump. As you add more insulation, you'll get increases, but they tend to be smaller incremental gains. The other thing to look out for is if you're dealing with UL fire rated designs like this open web truss, there's often a maximum thickness for your insulation. And if you go beyond that, you have to change things about the assembly. Typically, that's reducing your channel spacing. So by increasing the insulation, you may incur other costs, material and labor costs, because you've got to add more channel to your ceiling or something like that. Okay, the last 2 things I don't have examples of because they can be a little bit more complicated. So one is stiffness. So if we're looking at, a lightweight joist floor, it can be fairly flexible. And if it's flexible, when you walk on it, it's easy for it to bounce and move and create sound. And if we stiffen it, often it can perform better. That really gets more into some kind of structural considerations and things like that. So know that that's a tool that can be used, but probably something to consult, a structural engineer and an acoustical engineer. Damping is another thing, and damping can range from something that's fairly simple, like an off-the-shelf sort of constrained layer damped gypsum board product. But it can go all the way up to, a tuned mass damper at the top of some big tower, right? And there's all kinds of different ways that we can apply damping. Really, it's like the shocks on your car. It just resists that motion, so it kind of smooths it out. Like if you've ever seen a car going down the highway, going over a bump that's got blown shocks, it just hits the bump and it just keeps bouncing, right? But as the shocks you bounce, and you kind of level out. That's what damping does sort of acoustically in these assemblies, is it just slows down that vibration so it doesn't keep going as long. Again, can be a more complicated thing. Depending on the application, it's worth talking to an acoustical engineer about or something like that to get some guidance. All right, so in conclusion, code requirements for multifamily, right? STC and IIC 50, Those are minimums. Those ratings have their limitations. IIC limitations really are significant, I think. The HIIC and the LIIC are good design tools that help address some of those limitations of the IIC rating. Ceiling isolation can really help with better HIIC and LIIC ratings. Flooring and underlayment really does more for HIIC predominantly. Again, the code requirements are minimums. They don't guarantee satisfaction. And to that point, here's this quote again, right? The current level of performance specified by the building code, a large percentage of people are highly annoyed by noises from their neighbors, leading to reduced quality of life and possibly to negative health effects. And with that, thank you for listening, and we will open it up for questions now.
Thank you, Mike. So yeah, if anybody has questions, please, you can either drop them into the chat or feel free to speak up on the call.
So I see a couple here from Alan Kirshner. Okay, so from 10 minutes ago, is the industry working towards testing standards that will address the shortcomings of the current STC IIC standards beyond LIIC and HIIC? How about the walls, STC? Yeah, great question. So, and let me, bad types of material. Okay, so the other one's a different subject. So we are working on other testing standards. I would say that there's, so this is a long conversation, but there is some work. There's a lot of discussion about the need for that, at least within ASTM. And in different places, there are some people doing some research into that. There's a PhD student who was at Michigan Tech. I think now he's at Penn State, who's doing a lot of research into building acoustics. But generally in the United States, we don't have a whole lot of like funding and research into building acoustics and noise control. And really where that kind of standards development or the test standard development comes from is, more academic research. And we don't have a whole lot of that in the United States. And so a lot of it has fallen on manufacturers to go do testing, and try and update and improve these standards based on our experiences in the labs doing testing. So there is some movement in that regard. I'm actually working on using delta vibration measurements to predict impact sound pressure levels. I'm presenting on that at the ASA conference next month. I don't know if that'll be a better method or not, but it might be a helpful design tool. And for STC, there's talk there. I would say for STC, I have more of the limitation is just the limited frequency range, less sort of some of the other measurement methods and things. And so like one of the reasons I wanted to show these graphs and sort of like more of the details that goes into these is that if you really want to do a good design, if you look at it in terms of the third octave band data, the TL values or the impact sound pressure level values, you get a better idea of what that assembly is doing and you can come up with better designs, especially if you're doing something, you're dealing with noise sources that are outside of the typical like footsteps or like speech. So if you're dealing with, a music venue or a band practice room or something like that, you should really be looking at the third octave band transmission loss value for your assemblies rather than just STC ratings. The next question, also from Alan, what has your research shown in the comparative acoustic performance of various bat type materials in assemblies? So on that, I got to give a shout out to Pabco Gypsum and Quiet Rock, who's actually Steve's former employer. Their acoustician, Ben Schaefer, has done a lot of testing, and he's done some stuff looking at like fiberglass bat insulation versus, mineral wool, rock wool. And those are the two main ones that I remember talking to him about. And really, I think for the most part, the difference is negligible. There might be some instances where you see some differences, but they tend to be small, and I think they're sort of within the uncertainty or the test variability that we have. So I have always had the opinion that it doesn't make sense to like spend more money on some type of insulation because the benefits are small or negligible. Some people have different opinions, but the data I've seen makes me think it's not worth, there are more important things to worry about. Anything else? And also, yeah, feel free to throw something in the chat, or just unmute yourself and jump in and ask a question if you like. And while we're waiting, I will just give a plug here. So one question that comes up is like, well, okay, so if I need to get data for an entire assembly, where do I get it? Where do I get STC and IIC ratings, and where do I get this additional information? So we've got a tool. It's our assembly selectors. We have them for floor ceiling assemblies and wall assemblies. The link to register is there up at the top. If you go, click on it, give us your name, email, that basic stuff. And then we're pretty quick to approve you, usually within like 24 hours. And you can get in here. So you can sort and filter by like construction type, STC and IIC ratings, floor finish, UL assemblies, all these different things. And then you can come and grab these tools like these one-page summaries that you can put into your project documentation. And if you're in here and you're looking for stuff and you can't find it, or you find something that's close but you want to tweak it, please feel free to reach out to us. I can help work through those things. And maybe I've got something that's just not up there yet that's closer to what you need, or I know somebody at another company that's got data for it, or maybe we're interested in going to testing it if it's an interesting assembly for us, or a big project that warrants it. Somebody asked, Blaine Paxton, great presentation, thank you. Will a copy of the presentation be made available? We are recording this. I don't know that we'll put this version up, but there is already a version on our website. Let me see if I got a page here. No, but if you go to PAC International LLC, there's like a webinars videos link up at the top. If you go to that, there's a recording of this. You can also find us on YouTube. We've got a recording of this presentation up there as well. And also, while I got it up as a reminder here, we do have another course through AEC. If you need some more AIA credits, this is also HSW qualified credits. It's actually 1.5. And it's an online, like self-paced thing. You just go through, read a bunch of slides, and then like take a quiz at the end. So you can kind of do it on your own time, do it at home, whenever you got some time.
Okay, anybody else have any questions?
Oh, Alan's got another one. How does cost and performance compare between RIIC versus pads and RC? I'm guessing, Alan, for the pads, are you talking about our RC boost? Or some other kind of thing and
yeah, your
channel?
boost. Yep, the boost. Yep.
Okay, so there's a couple things. So cost, our boost is really inexpensive. I mean, it's like if you're buying it in volume, I think the retail price, and we have actually a where to buy thing on our website, so you can go see retail pricing for our products. Oftentimes that's helpful for people if you're reviewing bids and things. The boost is like 46 cents a piece. If you're doing spacing of like 16 inches by 24 inches, it comes out to like something like 17 cents a square foot. So it's pretty inexpensive. The cost of the resilient channel varies regionally and depending on brand and manufacturer. So I don't really know, but it's pretty inexpensive too. The RIIC clip is definitely more money. We say it usually comes in around like $1 a square foot. But the biggest, so sometimes like in a direct comparison on an open web truss, I've got gypsum concrete and I've got resilient, I've got the RIIC clips on one and I think just regular RC Deluxe on the other. There's like a 5-point difference there. Adding the boost to RC Deluxe actually can get it up close to the performance of the RIIC 1 in the lab. But the thing with resilient channel is that it is very prone to installation errors. And so when we go do a lab test with resilient channel, whether it has our product in it or not, right, I am overseeing the installation of everything to make sure that it's done right. I was a consultant for 10 years. I would go do a lot of site walks at apartment buildings and, GSA projects and all kinds of different things. I don't think I ever went out to a site where I saw resilient channel installed correctly from the get-go. Like I was always making changes to it. I don't think I ever saw a situation where clips were installed wrong. So the big performance difference between the RIIC clip and like resilient channel, even with the boost, is the RIIC clip is like the quality assurance of performance in the field. And there's a great, if you're interested in the issues with resilient channel, both from a design standpoint and a construction installation standpoint, ABD Engineering and Design, acoustical consulting firm here in the Portland area, my former employer, they've got 2 blog posts about resilient channel that are really good. You can just Google ABD Engineering resilient channel and you should be able to find them.
Okay, anybody else have any questions?
All right. Nothing. Well, thanks everybody for joining us. We've got our basic email there, our website, phone number. If you got more questions, feel free to reach out. Like I said, there's already a video of this up on our YouTube and our website. And we will be doing another one of these this afternoon if you know anybody that would benefit from it. And we've got another one coming up, I think December something. I can't remember when. I should know, but you'll find it on our website and we'll blast it on LinkedIn and all that good stuff.
December 15th, Mike.
Thanks, Steve.
Yeah, no worries.